welcome again to the new lecture of this course, Solar Photovoltaics Principles, Technologies and Materials. So, we will do a quick recap of last topic. So, in the last class we talked about CDT solar cells, the remaining parts of processing, and then how to make improvements. So, one was CDCl2 treatment, copper doping at the back contact, and prevent interdiffusion between CDS and CDTE. So, these are few methods which can improve the process, and then we saw the efficiency of this is about 21%. The best efficiency is obtained. These are device level efficiencies, not the module level. Module level efficiencies go a bit lower. However, this is a very promising technology for the future. Now, we discuss another technology which is basically we can say copper, basically copper indium selenide, but it is doped with generally. So, essentially it is copper indium gallium selenide, or it is also called as CIGS solar cells. Now, on this technology the work started in 1970s in Bell Labs in USA, and 12% efficiency straight away in 1975. So, very quickly the efficiency improvement was observed, and in 2005 we had 19.5% efficiency, and today we stand above 20% in so 2018 it is more than 20% efficiency in thin film solar cells. These are essentially thin film solar cells. So, thin films of CIGS are used as primary absorber. Okay. So, the typical device structure in this is you have soda lime glass, It is important to choose soda lime glass, not any other glass, because as I will show later, because it improves the performance. And then we have a moly layer on top. So, here molybdenum is used as a contact, which is about half a micron thick, and then we use a layer of CIS or CIGS, about 2 micron. Okay. And then on top of it, just like cadmium telluride, we use a thin layer of cadmium sulphide window layer, which is about 0.05 micron or about 50 nanometers. Then again on top we use a high resistance oxide layer, so HRO, which is generally zinc oxide layer of about, this is a little thick, half a micron or so, and so basically generally it is a junction. It could also be a junction of zinc oxide and N plus zinc oxide. So, it is possible that could also be a, sorry, let me use with ZNO, which is high resistance, then N plus ZNO junction, and then on top we have contacts. Top contacts, you can say this for current collection, which could be a metal like it could be, I think, aluminum. You can use aluminum on top. It could be a metal like aluminum, or I don't know, silver. Various other metals are possible. So now let's see first what is this material all about. So first we look at the material aspects of CIGS. Why we use CIGS is because you can vary the ratio of with large tolerance. And this is basically used to tune the band gap. So when you change the indium to gallium ratio, it leads to changes in the band gap. Also in CIGS, grain boundaries generally are, these are polycrystalline films most of the times, grain boundaries are generally passive. So as a result, they don't lead to too much of damage to the device. So you can use a smaller grain sizes because the grain boundaries do not deteriorate the performance because of their passive nature. And generally the junction between CDTS and CIGS is pretty good. It doesn't, the junction behavior in terms of defects does not cause major change to the device performance. So these are few aspects of CIGS which are pretty advantageous, that the grain boundaries are passive and junction metallurgical behavior of the junction does not affect the device performance that much. So what is now CIGS? CIGS has a band gap. So if you look at CIGS, CuIn1 minus X, GaX Se2, the band gap of this material is given as 1.01 plus 0.626 X minus 0.167 X into 1 minus X. So if your X is 0, so CIS has a band gap of 1.01 eV. This is an EV, okay. And for CIGS, this band gap changes as you increase the, so you can see as you increase the value of gallium in it, according to this formula, the band gap will change. So if you, for instance, if you take a value of, let's say, so if you take a value of, for example, 0.1, if you take gallium to be 0.1 or X to be 0.1, the band gap could be 1.01 plus 0.626 minus of 0.167 into 0.1 into 0.9. So you will increase the band gap by doping it with, so band gap changes significantly as you put in gallium in it. So gallium's band gap would be GaSe2 band gap would be, so if you, let's say, put X is equal to 0, X is equal to 1, if you put X is equal to 1, instead of doing this, let's say we put in X is equal to 1. If you put in x is equal to 1, then Eg would be 1.01 plus 0.626 plus 0. So, this is 1.636 eV. So, you can say based on this formula, the band gap will change between 1.01 EV to 1.6 EV by changing the indium to gallium ratio. And we know that our ideal band gap requirement is about 1.4 electron volt, but you cannot keep increasing the gallium values too much because it also leads to changes in the resistivity of the material. However, we can tune the band gap by changing the different indium to gallium ratio in the material, and that is why this gallium is doped in indium gallium oxide. So the band gap for CIGS for commercial application has a band gap between 1.01 to 1.1 EV, that is what is typically used. It has a melting point of about 985 degrees centigrade. So, and basically it's a material with complex structure. It's a chalcopyrite kind of material. So, it's a, you can say it's a chalcopyrite structured material. So, it belongs to the chalcopyrite category. Presence of 4 elements make the presence of makes processing challenging because the phase diagram is complex. So, generally we look at a phase diagram. If you look at CIS, in the context of CIS, we generally look at a pseudo binary diagram of between Cu2Se and In2Se3. But when you go to ternary phase diagram, then we have so now we have CIGS. So, this gives rise to a pseudo ternary phase diagram. Okay. And this leads to complexity in understanding the phase formation. So, you do not have too many degrees of freedom to optimize the phases. It is a little bit tricky in terms of, so, and also since you have so many elements, the defect levels also get created quite a bit. So, for example, in this case, if you have vacancy of copper, the vacancy of copper leads to, it makes a shallow acceptor. If you have indium sitting on copper site, you have, it makes it as a compensating donor. If you have selenium vacancy acts as a donor, compensating donor. And if you have copper on indium site, this acts as a recombination center. And if you look at the values here in terms of energy levels, this creates energy level EV plus nearly 0.03 EV, it is very close to valence band. If you look at this, this creates energy level EC minus 0.25 EV. This is probably roughly the similar, and copper indium is about EV plus 0.29 EV. So, these are different energy levels that one can create within the CIGS band structure by putting impurities. There are various other things which are possible. You can have indium, so you can have copper interstitials also. So, it is possible to have copper interstitial. It is also possible to have vacancy of indium. It is also possible to have, and these vacancies may also exist in partially ionized or completely ionized, and as a result of that their energy levels will vary. Similarly, here it will be partially or completely ionized. So, there are a variety of defects which are possible in this structure, As a result, the compositional control is little difficult in this material. However, generally we say this material is p-type in nature, so it's generally p-type CIGS, and the p-type behavior is achieved mainly from copper vacancies. So, copper vacancies, you will have VCU, which is negative in nature, plus hole, 2 holes. Okay. So, this is what will give you. So, copper vacancies are the main source of p-type behavior, and it is generally easy to make a p-type CIS than n-type CIS. The carrier density in this system is about 10 to the power 16 to 10 to the power 17 centimeter cube per centimeter cube. Electron mobility is about 90 to 900 centimeter square per volt second, whereas hole mobility is about you can say 5 to 50 centimeter square per volt second. So, this is in polycrystal. In single crystal, these values would be from 5 to 200. This is also in single crystal. In polycrystals, these value will change to about 500 or so. So, generally 50 to 500 in polycrystal. So, these are not too bad values, they are better than, for example, if you looked at the values of polycrystalline silicon, they are better than polycrystalline silicon values. So, it is not a bad material in terms of electrical behavior. So, generally generally we can say CIGS is generally p-type material, and that is why instead of making this as a n-type, we use CDS as n-type material to make a PN junction. All right. And these devices, since you have selenium in it, the content of selenium plays a very important role in controlling the electrical properties of material. So, when the films, as we see, are annealed in selenium vapors to achieve good properties. So, if you look at the absorption behavior, the absorption behavior of material is very good. So, if I plot alpha as a function of energy in EV, so around 1.52, it has a band gap of nearly 1 electron volt. So, it gives you absorption which is as good as 10 to the power 5. So, the values reach about 10 to the power 5 centimeter inverse in the useful range. So, it is a very good absorber of light, excellent. Light absorber. So, most of these materials are very good absorbers as against silicon. Now, typical devices in this case, the devices have, so in devices, the grain sizes are of the order of about a micron. This is the typical grain size in the device that one obtains. Composition also changes slightly from surface to bulk. So, there is a compositional gradient from surface to bulk, and this basically improves or decreases, you can say, surface recombination because if you have composition changes, you will have energy level changes. As a result, the carrier velocity is not very high, and these devices are generally post annealed in selenium. To control the selenium content, and they are deposited on soda lime glass, and this is because sodium helps in surface passivation. So, it controls the surface passivation by controlling the dangling bond density, and it also controls the cell helium vacancies. And so, soda lime glasses are useful in these devices. So, generally, and also its coefficient of thermal expansion alpha thermal matches with that of CIGS. So, thermal stresses in the devices are lower and you have less cracking in the thin films. And the back contact, as we said, is molybdenum, which is quite thick, and molybdenum is one of the most successful materials used with CIGS. And at the back there is a formation of MoSe2, which seems to improve the adhesion of these devices. So, how do you make CIGS? Let us first look at that. So, CIGS is made by, so CDS of course as we said is made by chemical bath deposition or sputtering, okay, and it is a very thin layer. How do you make CIGS? CIGS is, so CIGS manufacturing, the first process that we take is the co-evaporation. So, what you do in this, that you have a chamber. So, this is the chamber. On you have 4 sources. So, one source, second source, third source and fourth source. They may be concentric sources basically. So, sort of in a concentric. So, you have well, let me put it this way. If you have this as a, so one source will be here, another source will be here, another source will be here, and one source will be here. They are all pointing towards the substrate. So, these are 4 sources, you can say evaporation sources. And then we have substrate held at high temperature, and then you have somewhere here you have a, you can say there could be a growth monitor. So, as you apply electricity to these, as you heat them, there will be evaporation of, so this would be for example copper, this would be indium, this would be gallium, this would be selenium, and of course, it is connected to a pumping system. So, you co-evaporate these things together. So, evaporation temperature of, for example, if you look at the evaporation temperatures, copper is about 1300 to 1400 degrees centigrade. Indium, this is in vacuum by the way, right, 1000 to 1100 degrees centigrade. Gallium would be 1150 to 1250 degrees centigrade, and selenium would be 300 to 350 degrees centigrade. So, they are all evaporated. See, when things evaporate, they get deposited on the substrate, but there is also a re-evaporation that may occur. So, you may have a sticking as well as you have re-evaporation. So, the deposition rate will depend upon what is the sticking coefficient. Okay. There is something called as a sticking coefficient, which determines the ability of elements to stick on a surface or deposited on a surface. Generally, what happens here is the elements like selenium, they are volatile elements. So, selenium volatile, being volatile leads to selenium vacancies. So, this may require you to do a post heat treatment in selenium, because selenium has high vapor pressure because of its low melting point and boiling point, As a result, it tends to get depleted from the devices, and hence it may be required to form selenium in sufficient quantities. Also, indium and gallium may also be lost from the films, and this is mainly because indium and gallium tends to make compounds like IN2CE and Ga2SE. So, this leads to loss of indium and gallium in CIGS. Okay. So, instead of forming the CIGS phase, they tend to form these other phases. So, phase formation is very critical in this. The good thing about this process is you can control the evaporation rate and tune the film composition and the band gap by choosing the heating rate of each of the sources. That is possible, and it is also used to make good quality devices. And for a 2 micron film, one can use the deposition rate from 20 to 200 nanometer per minute. So, it can be very fast, but making large area devices is a problem. Evaporation is generally a small area process. So, large area is an issue. So, generally so people also follow what we call as a two-step process. So, in this two-step process, first one deposits deposition of indium and copper layers or copper indium layers, followed by then you heat treat in selenium environment. Okay. This deposition of these layers is done by either sputtering or electrodeposition or one can do evaporation, E-beam evaporation for example, or even screen printing. Okay. Selenium treatment is done in an atmosphere which is hydrogen selenide atmosphere, or selenium vapor at about 400 to 500 degrees centigrade. One can also add gallium in this process, and gallium, so you can co-evaporate gallium when you make indium and copper layer and then do the selenization treatment. So, gallium can go in this stage. Generally, gallium addition leads to some accumulation near molybdenum electrode, and what forms there is generally you can form a junction which is CuInSe2 / CuGaSe2, and this would be near MO. So, it would be like that. So, near MO first you have CuInSe2, then you have CuGaSe2, then you have CuInSe2. This tends to improve the adhesion. Okay. So, this is sort of a graded junction you will make. So, first a layer of CuGaSe2, then you have a layer of CuInSe2. You can do it this way, but you can also do it together. Generally, it is formed if you have a graded junction like this, then voltages are higher. It is a very well standard process. The problem with this is since you deposit these things together, the control of composition is an issue. So, issue is as compared to evaporation, where you can evaporate independently and control the composition, evaporation rate, and hence the composition. So here and also this H2SE is hazardous. There are other processes one can use, which I am not going to go into details. So one can use reactive sputtering. Just like co-evaporation, you can do reactive sputtering. One can do closed space sublimation, which is a close cousin of evaporation. Then one can do chemical bath deposition. By using appropriate starting materials. You can also do laser evaporation or laser ablation, and one can also make them using spray pyrolysis, just like we made CDT thin films. However, in all of these processes, as compared to CDT, composition control is tricky, and this is because you have 4 elements. So, choice of temperature, time, ambient is the key to phase formation. So, choice of growth temperature or heat treatment temperature, the time, and the ambient, what kind of ambient you have. And this is where your knowledge of phase diagrams is very important. So, you need to understand, we do not have unfortunately time to go through the details of phase diagrams, but to understand phase diagram is important. So, we will stop here today. We have done some introduction to CIGS. We will look at some more details in the next class before we switch on to the next third generation technologies. Thank you.